Hi everyone, I'm Balaji. I'm Dr. Balaji Muthusubramanian. I am an astrophysicist. I did my bachelor's in physics. I did my B.SC physics here in Vivekananda College in Chennai. And then I moved to Netherlands to do my master's in astronomy at University of Groningen in Netherlands. And then after my master's, I moved to Germany, University of Cologne in Cologne, Germany. I did my Ph.D. in astrophysics in Germany, and I worked for telescopes in Chile, very large telescope interferometer, and also in Spain, the Grand Telescope Canarias, Isaac Newton Telescope, and William Herschel Telescope. So I was part of the instrumentation team over there, and I was mainly working on star and planet formation and exoplanets. So that was mainly my expertise. And today I will explain to you about how a telescope functions essentially and what kind of telescopes are there, more from an optics perspective and a bit more on the astronomical perspective. So essentially, if I want to start about telescopes, I mean, we all know about it that the main reason why we use a telescope is to view distant objects. Now, often I get asked this question. So I'm an amateur astronomer as well. So I've been into astronomy since I was 10 years old. So I'm an amateur astronomer as well, and I've been handling telescopes like, I hope you can see this, like what is over here. I've been handling telescopes like this one since I was 10. So usually the question that anyone, even recently they've been asking me the same question is, how far can you see through a telescope? Now, if you look at it from an optics perspective, right, technically it's infinity. If you have an eye strong enough, you can see till infinity. So the whole concept of the reason why we use a telescope is to see distant objects nearby. Now, okay, that technically it goes all the way till infinity. So what limits? So why are we still building bigger and bigger telescopes? So why can't I still do all my astronomy, all my research with this guy down here? What is the difference between all these things? So there are a few factors. So let me first explain the theoretical part of it. So the main concept of a telescope is basically to focus objects on infinity, bring that image to focus objects on infinity and bring that image to nearby so that you can magnify and see the image. So the main concept is I have, well, a star at a distance, okay, let's say at infinity, and then I've got my magical telescope over here. Now all I have to do is get this image of star over here and magnify it so that when I view it through my eye, I should be able to see this distant star with all its details over here. So this is the whole concept of why we need a telescope. Now that means essentially now if we go by optics, right? So the whole point is, okay, I'm getting light rays from infinity that comes here, and then my telescope must do some magic around here to focus it there. So by focusing, what I mean is once it hits the telescope, it has to, sorry about that, has to focus right over there. So then I can take it forward and go ahead with my observation. So now what can I use? What goes in between? Now if we look into our basic optics, if I just put a convex lens over here, well, ta-da, I'm already done. There's my telescope. Well, does that mean that, okay, this is what I'm going to see? No, because this is like infinitely, I mean, it is focused, but it is small. So I need to magnify it. So to magnify it, I usually have a second lens over here, which then takes this thing, focuses it back to my eye. So it magnifies it. Now this part is something what we call as an objective, and this part is something that we call as an eyepiece. So this is what is telescope all about. And as soon as I say the word telescope, the name that comes to everyone's head is Galileo. But actually Galileo was the first person to use a telescope to look at the night sky. But Galileo didn't come up with a telescope. It wasn't Galileo. Galileo just used it to look at the night sky. The first one who built it was a person named Hans Lippershey. Hans Lippershey built the first ever telescope, and back then the mariners used to use telescopes just to see if there is a land at the distance. So mariners used telescope. So Hans Lippershey was the first one who built a telescope. Galileo in 1609, he basically used this telescope to look into the night sky. So so back then telescopes were mainly made out of two lenses, what we have learned in our textbooks. Now this is what we call as the Galilean or refracting telescope. So we call it Galilean, Galilean or refracting telescopes. So the whole concept is, well, the light comes in, you refract, you focus, and then you have an infinitely small image, and then you place an eyepiece, so you magnify it, and you can see it as if it's right in front of you. Now it doesn't have to be star, it can be any distant object at infinity. So now before I go into the other parts or the other components of the telescope, let me first answer this age-old question that I've been getting ever since people knew that I had a telescope or I was using a telescope or I'm an astronomer. The age-old question is, okay, how far can you see through a telescope? So technically, if you look at it, it's an object at infinity. As long as I get light hitting here, as long as I can have photons hitting my objective, I'm good. That means even a single photon that goes through this, it's going to focus in and I'm going to have an image. So, I mean, technically not a single photon, but I mean, if I have a handful of photons, I can still get an image. Now, then why do we need bigger telescopes? Or why can't I see the most distant object in the universe? Like if I just point a telescope somewhere, can I see a distant object in the universe? The answer is no. The reason is not, the problem is not with the telescope, but it's a problem with our human eye. Now, our human eye actually has only a certain capabilities, as in it has like if I want to say it in say more like a camera perspective, we have a fixed frame rate. So our eyes it takes images in a fixed rate, which means our eyes only has a certain level of sensitivity. It doesn't have as much a sensitivity as say certain predators out there. They have better sensitivity than us. So I'll teach you a few tricks and things around how our human eye evolved to look through the night sky. But let's get back to our telescope, and then I'll come to this part in later on, or probably in another video. So as I said, it's a refracting telescope. So Galileo, everybody used it for about 100 years. And then came 1700s. And usually, you know, it's like everything, like our smartphones to everything. After some point, we get bored of it. We start seeing faults in that in the system, right? So with the Galilean telescope, we actually saw what was going wrong with it. So what went wrong is the lens over here. So I can take this lens, I can deconstruct this lens into three components: two prisms and a rectangular glass slab in between. If I want to like say do it as a 8-bit kind of lens, yeah, it's two prisms, triangular prisms, and a lens and a glass blank in between. Now, as we already know, if a ray comes through this, then we already know what's going to happen if it goes through a prism. You're going to see all the 7 colors. And it's the same thing is going to happen over here. So you're going to start having what we call as chromatic aberration. Chromatic aberration. But is it just chromatic aberration? There are a few more aberrations. You have coma, you have astigmatism, and so on. So there are all these aberrations which messes up my image quality. Now this is one part of the problem. The second part of the problem is I can only make lenses to a certain diameter. Now I'll explain why the diameter plays a role over here. Let me first finish this and I'll come to the diameter part. So now I can't build a lens large enough. So the larger the lens I build, the more expensive and the more heavy, the more brittle it gets, and so on. So which means I have a limitation on how big I can build this. And also on top of it, I have all these kind of aberrations. So what happens if I see, let me explain what happens on a chromatic aberration is that if you use like a really a horrible camera lens, a DSLR lens or anything, if you use a really horrible lens, around the edge of the object, you'll start seeing colors around it. That's chromatic aberration for you. So basically, if I want to look at a star, if I want to look at a moon, or me being an astrophysicist, I care about the color of the object, because the color of the object tells me the properties of it. For example, if I'm looking at a yellow star, then it's what we call as a K-type star. Now a K-type star is typically 6,000 degrees, it has a certain properties, and it's like maybe it can also host habitable worlds and so on. Now this is essentially, so that means I care a lot about colors. We have red giants or blue supergiants and so on. So, or like say even colors point towards certain elements. If it's like super red, it's basically H alpha, which is 600 nanometers. So colors will tell me essentially the properties of the object. So color really matters over here. So which means we really can't go with chromatic a lens that has, or a telescope that has chromatic aberration. And the best part here is it's not just one, but I have two of them. Well, now you can say, hey, I remember in my physics classes, if I have one prism this way and I split up my light and I have, like, let's say I'm going to use a second prism, well, I'm going to go back to normal. Well, that happens in a good situation, but it's not always like the rays over here are going to end up over here and then comes back to you. It happens, but still it's a physical system. So that means we'll still have a lot of chromatic aberration still. Around the edges, I'm still going to see some colors, which I want to avoid in this situation. So this was a major problem till like they have noticed in the 1600s, and then came the 1700s during the time of Isaac Newton. So what happened was, okay, Isaac Newton basically asked this question. So all I have to do is, I have light rays coming from infinity, I need to focus it. Why do I need a convex lens for it? Can't something else do a better job than this? Well, the answer is yes. Instead of having a convex lens, let me draw the same star over here, or well, let's say another star. And here's my telescope. But what I can do alternatively is, instead of putting a convex lens over here, I can place a concave mirror. Essentially, I just need to converge the rays, right? So I can use a concave mirror and I can have my focus over here. But hey, you know, I can't keep my eyes over here because I'm going to block my star. I can't do that. So what we can do alternatively is, halfway through there, we usually place a secondary flat plane mirror. This is what we call as a secondary mirror, which then focuses this, focuses this light onto something over here, where I can place my eyepiece, which is again a lens, and I can view from here. So this is what we call as a reflecting telescope or a Newtonian telescope. So this is a reflecting / Newtonian telescope. So Isaac Newton changed the entire system from a Galilean system to a Newtonian system. Now, there are again advantages and disadvantages of this whole thing. Now, one major advantage is, well, I can get rid of, not completely, but at least 99% of my chromatic aberration is now gone. The reason why I had chromatic aberration in the first place is I have refraction and dispersion happening over here. In case of mirror, I only have one thing that happens, which is reflection. So reflection essentially doesn't do dispersion, but it has a few other problems, but dispersion is not the major problem in mirrors. Now, this is one way of, so this is what we call as a Newtonian telescope. And then there is a third kind of reflecting telescope called a Cassegrain telescope, which is essentially, instead of having it, now the problem with Newtonian telescope or even with Galilean refracting telescopes, so if you look into old school telescopes, right, from the 1800s, or even the observatories, they are humongous. Now, I have a telescope over here, which is, well, I can stand right next to it. But if I had a telescope of this diameter, it's about 20 centimeters or 200 mm in diameter. Now, if I have to have this telescope in the 1800s, I can't even fit this telescope in this room. It's going to be way massive. The main reason behind it is that back then, the focal length of all these telescopes were large. So you need to have a sufficiently large focal length, but also you can't have like super long focal length. Okay, two problems. One is you can't have a super massive telescope. At the same time, you'll also lose light along the way. I'll explain why so in a second. So focal length is a massive problem over here. So what happens with focal length is that, I mean, essentially the longer the focal length I have, so in telescope we have this famous equation, that is the magnification that I have of any reflecting or refracting telescope, the magnification that I will see of an object is the focal length of the objective over the focal length of the eyepiece. So that's how much I have my magnification. So for example, this telescope has a focal length of, sorry, I forgot. It has a focal length of 1200 mm. Now, if I combine it with my eyepiece over here, which is 20 mm, I'll have a magnification of about 600x. So 600 times I'm going to have magnification. So this is a 20 mm eyepiece. This is 1200 mm objective. So 1200 over 20. So no, sorry, 60x, not 600, 60x. So I'll have 60 times magnification if I use this eyepiece. If I switch it over to this guy over here, which is about 10 mm, I'm going to have 120x magnification. So that's essentially what happens. That's the advantage. So that means the longer the focal length I have, the better the magnification. But technically, we don't usually go for super long focal lengths. We usually go for something that is, handleable and easy for two reasons. One is we don't want to let our light travel for too much within the tube of the telescope, because what happens is it's not just the reflection, but you can also have scattering. You can also have like a lot other, say, what we call as white noise photons. That can be, some other light that comes from this direction hitting over here and interacting with our main source photon. So now the more the room I give, the more amount of mess that I'm going to have. So typically the longer the focal length, the lower is the quality of the image that we always see. And also the shorter the focal length on the eyepiece, again the quality goes down. So which means our magnitude, we need to keep it on a balance on this. So now coming back to our Newtonian telescope, now the thing is, the tube length is completely dependent on the focal length of the primary mirror. So the focal length is, well, this distance plus this distance. So that's my focal length. Now, which means my telescopes are going to be humongous and huge, and also I'm going to have a serious balancing issue, because this is where I'm going to put my science payload. So which means my telescope can easily topple on one side. Now this is a Newtonian telescope over here. So I'll show it in a second, if I can drag it here. So the thing here is, here's where the eyepiece is all about. So all that I can do, the science, or if I want to put my eyepiece or anything, all the magic happens over here. So if I want, I can keep this and use my eyepiece, or I can remove this thing off and load any science instrument over here, a camera or whatever, and I can go on with my observations, right? My measurements, whatever, my recordings, everything. Now the problem here is the more weight I put over here, the more I'm going to have an issue with my stability. Now I'm looking into a tiny patch in the sky, so even a small jitter, I'm going to shoot off from my object. So that's something that I badly need to avoid. So that's why we have a third kind of telescope, which is a Cassegrain telescope. So a Cassegrain telescope is essentially a similar telescope to a Newtonian. So I'll probably draw it over. Okay, let me just draw it here. So what a Cassegrain telescope does is that instead of a secondary plane mirror, I have a secondary convex mirror. So the advantage of a secondary convex mirror is that, and then I have an opening over here. So this is not a completely covered mirror, there is like a central hole. So the point with this Cassegrain telescope is that I'm going to have multiple reflections between my primary and secondary, and then it goes to the eyepiece. Now the advantage of this is that now I can pack up a massive focal length into a tiny package. So essentially I don't need to have a super long telescope. I can just pack it all up in a smaller tube, and I can still do my science. Now most of the observatories use a Cassegrain system because, well, there are two advantages. It's easy to handle and the payload can be used, and another trick is I can also like remove my secondary and I can add like a few more science instruments over here. So there are like a lot more advantages with the Cassegrain telescope. So this is essentially, say, the fundamentals of telescope. Now I just wanted to add one more thing, that is I was talking about the magnification of the telescope, but the magnification of the telescope is not the only thing that matters if you are looking into a telescope. It's not just the magnification that matters. It's also the resolution of the telescope that matters. So what do I mean by resolution is that if I have two stars, one right next to the other, or let me just draw it bigger for the camera, let me have two stars, one right next to the other. Now my telescope should have the ability to distinguish these two stars as two separate stars, not as one. Now what do I mean by this? So instead of ray optics, let me just do a little bit on wave optics on this. So the point here is, if I have two stars, one right next to the other, this guy is going to emit waves, and this guy is also going to emit some waves, right? Now if they are super close by, the phase difference between these two waves are pretty much negligible. Now our telescope should be large enough to identify this phase difference. So the point here is the phase difference between these two, the angle over here, the telescope has to be large enough to identify this thing. If not, typically so that's what we call as resolution. It has to identify split up these two objects as two separate objects. Now why do we really care about resolution? Well, let me say this way. One of my research work is about taking high resolution images of exoplanets. So one way of discovering exoplanets is by directly imaging them. So to directly image a tiny dust mote orbiting around a massive star, I need to have good enough resolution to work on it. Or I also, like most of the young stars, they prefer to form as binaries, as in two stars forming together. That means I need to resolve them as two separate stars to know what exactly is happening on each of them, to understand how the stars form. So for these things I need a good sort of resolution. So now typically for resolution, we have the equation that is like the minimum angle, that the minimum separation that I can have between any two stars. So let's say I have so this is my point of view. Now I have like two objects over here. The minimum angle that I can see, like that I can split up these two stars, is defined by this equation, which is 1.22 lambda over, this is the wavelength of the light, typically, now let's say it's green light, which is 500 nanometers, and the diameter of my telescope. So the larger the diameter of my telescope, the smaller is my resolution. That means the more details I can start seeing of the object. So the more details of the galaxies that I can see. So that's like a key factor. So anytime when you talk to an amateur or a professional astronomer about telescopes, they only care about the diameter of the telescope. Not many people care about the focal length. Focal length gives us magnification, of course, but magnification is something that not all of us are after. We are more into clarity than magnification, because magnification really doesn't matter, because all the objects in the sky are pretty massive. Now, if you look at, say, for example, Andromeda galaxy, it seems to be a far enough object that you need a telescope to see. Not exactly. If you look into the angular size of Andromeda galaxy, it's about 2 degrees. So the angle, like if I have the Andromeda galaxy and I'm looking at it, this angle is about 2 degrees. Whereas if you actually see the sun or the moon, this is half a degree. It's about 30 arc minutes. So that's why so Andromeda is like about what? About 4 times bigger than the sun and the moon just by our eyes. So if you are in a dark enough sky, you can still see Andromeda galaxy without a telescope. So most of these objects in the night sky are humongous that you don't even need a telescope in the first place. So you don't really always need a telescope for astronomy. But if you do, like say if you want to look into why do I want to see Jupiter? I don't want to see Jupiter bigger. I want to see the cloud patterns on Jupiter. Of course, I will see it bigger because whatever it is, there's going to be a focal length, so there will be some magnification. Now, what I really care about is, can I see the cloud patterns on Jupiter? Can I see the rings of Saturn? Can I see the Cassini division? That is like a small gap in the rings of Saturn. Can I see how the craters are structured on the moon? Am I able to see, say, the polar caps on Mars and all these things? Now, if I just want to talk about the solar system, right? Or can I resolve like individual stars on the Andromeda galaxy? So this is where resolution plays. So we care a lot about resolution because that's where it is. It's all about quality. I don't mind watching a 4K video, okay, on a massive TV. I don't mind watching a 4K video, but I don't want to buy a massive TV and watch a 720p video, right? Now, I want to see it in 4K. So that's why the diameter of the telescope matters. So the larger the diameter of the telescope it is, the better it is. Now with refracting, we can't build a large enough lens, but with reflecting, we can build, and now say we are building the European Extremely Large Telescope, which is about 42 meters in diameter, which is almost the size of one tennis court. That's the diameter of the European Extremely Large Telescope that is coming up in Chile right now. So now that being said, I think we'll close this video now with, so I think I've explained the fundamentals of the telescope. So in the next video, we can deep dive a bit more into telescopes.